Right now, at this very moment, you are sitting somewhere. Maybe on a chair, maybe on a bed, maybe on the floor. And you probably think the reason you are not falling through that surface is because solid objects cannot pass through other solid objects. That sounds obvious, right? That sounds like common sense. But here is the thing. That explanation is completely wrong. The atoms in your body and the atoms in your chair are mostly empty space. More than 99% empty space. If atoms were actually solid little balls touching each other, that would be one thing. But they are not. They are almost entirely nothing. So why do you not fall through? Why does matter feel solid when it is almost entirely vacuum? The answer to this question is one of the most profound and mysterious rules in all of physics. It is a rule that has no known enforcer. There is no particle carrying this rule. There is no force implementing it. And yet, every single fermion in the universe obeys it without exception. This rule says that no two identical fermions can ever occupy the same quantum state at the same time. Ever. And today, we are going to explore this rule from every single angle. We are going to understand where it came from, who discovered it, what it means mathematically, what it means physically, and what would happen to the entire universe if this rule suddenly stopped working. We are going to travel from the inside of atoms to the cores of dying stars. We are going to explore why chemistry exists, why matter has volume, why neutron stars are so incredibly dense, and why you do not collapse into a point. This is going to be deep. This is going to be detailed. And by the end of this journey, you will never look at the physical world the same way again. Before we dive in, let me give you some numbers that will blow your mind. If this rule did not exist, every atom in the universe would collapse to roughly the same tiny size. There would be no difference between hydrogen and uranium. The periodic table would not exist. Chemistry would not exist. Biology would not exist. You would not exist. Stars would not shine the way they do. White dwarf stars, those dense remnants of dead stars, are literally held up against the crushing force of gravity by this rule. Not by heat, not by radiation pressure, by the simple fact that electrons refuse to be in the same quantum state. Neutron stars, objects so dense that a teaspoon of their material would weigh about 6 billion tons, are held up by neutrons obeying this exact same rule. And here is perhaps the most mind-bending part. Nobody knows why this rule exists at a deep intuitive level. We can prove it mathematically. We can show it follows from the structure of quantum field theory and special relativity. But when Richard Feynman, one of the greatest physicists who ever lived, was asked to give a simple intuitive explanation for why this rule exists, he said he could not do it. He said it appears to be one of the fundamental facts about nature that simply is. So if you love the kind of content that takes you deep into the mysteries of the universe, if you love understanding reality at its most fundamental level, then you are in the right place. Hit that subscribe button and that notification bell, because this channel is dedicated to exactly this kind of deep exploration. Leave a comment telling me what you think the deepest mystery in physics is, and give this video a like if you want to see more content like this. Now, let us begin at the beginning. To understand why fermions need permission to exist in the same place, we first need to understand what particles actually are in quantum mechanics. And this is where our everyday intuition starts to fail us completely. In our everyday experience, objects have definite positions, they have definite velocities, they have identities. If I have two tennis balls, I can put a red dot on one and a blue dot on the other, and I can always tell them apart. I can track which one is which. They are distinguishable. They have individual identities. But in the quantum world, this is not the case. Two electrons are not just similar to each other. They are not just hard to tell apart. They are fundamentally, absolutely, completely identical in a way that nothing in our everyday experience ever is. There is no property you could ever measure, no experiment you could ever do that would allow you to tell one electron from another. They have the same mass, the same charge, the same spin magnitude, the same everything. They are identical in the deepest possible sense of that word. Now, you might think this is just a practical limitation. Maybe they are different, but we just cannot measure the difference. But quantum mechanics tells us something much more radical than that. It tells us that there is no difference. The universe does not assign hidden serial numbers to electrons. There is no underlying identity. If you swap two electrons, the universe is in a state that is physically indistinguishable from before. This is not a statement about our ignorance. This is a statement about reality itself. And this fundamental indistinguishability of particles is going to turn out to be absolutely crucial for understanding why the Pauli Exclusion Principle exists. Because when particles are truly identical, quantum mechanics places very specific constraints on how their combined wave function can behave. And those constraints lead directly to the rule we are exploring today. Let us talk about wave functions for a moment. In quantum mechanics, the state of a particle is described by something called a wave function. This is a mathematical object that contains all the information about the particle. It tells you the probability of finding the particle in various positions, with various momenta, with various spin orientations. The wave function is not the particle itself. It is a complete description of the particle's quantum state. Now, when you have two particles, you need a wave function that describes both of them together. This combined wave function depends on the properties of both particles simultaneously. And here is where the magic happens. Because the two particles are identical, physics demands that the wave function must behave in a very specific way when you swap the two particles. There are only two possibilities. When you swap the two identical particles, the wave function either stays exactly the same or it picks up a negative sign. It flips. That is it. Those are the only two options that are consistent with the particles being truly identical. If the wave function stays the same when you swap the particles, we call it symmetric. Particles that have symmetric wave functions are called bosons. If the wave function flips sign when you swap the particles, we call it antisymmetric. Particles that have antisymmetric wave functions are called fermions. And this is where things get incredibly interesting. Because if you have two fermions in exactly the same quantum state, and you swap them, then on one hand nothing should change because they were already in the same state. But on the other hand, the wave function must flip sign because they are fermions. The only way both of these things can be true simultaneously is if the wave function is zero. And a zero wave function means zero probability. It means that configurations simply cannot exist. It is not unlikely, it is not rare, it is impossible. The probability is exactly zero. This is the Pauli Exclusion Principle. It emerges directly from the anti-symmetric nature of Fermion wave functions. But now we need to take a step back and ask, why are some particles fermions and others bosons? What determines which category a particle falls into? And the answer is one of the most surprising connections in all of physics. It is spin. The intrinsic angular momentum of a particle determines whether it is a fermion or a boson. Particles with half-integer spin, that is spin 1/2, spin 3/2, spin 5/2, and so on, are fermions. Particles with integer spin, that is spin 0, spin 1, spin 2, and so on, are bosons. This connection between spin and statistical behavior is called the Spin-Statistics Theorem, and it is one of the most profound results in quantum field theory. Now, Spin is one of those quantum mechanical concepts that is incredibly easy to misunderstand. The name itself is misleading. When we say an electron has spin, we do not mean it is physically rotating like a tiny spinning top. That picture is completely wrong. If the electron were actually spinning, given its tiny size, its surface would have to be moving faster than the speed of light to produce the observed angular momentum. That is impossible. So spin is not spinning. Then what is it? Spin is an intrinsic form of angular momentum. It is a fundamental property of the particle, like its mass or its charge. It does not come from any physical rotation, it just exists as a property of the particle. It is angular momentum without anything actually going around in circles. This sounds bizarre, and it is. But the experimental evidence for spin is overwhelming. The discovery of spin came from an experiment performed by Otto Stern and Walther Gerlach in 1922. They sent a beam of silver atoms through a non-uniform magnetic field. If the atoms had no angular momentum, the beam should have passed through without being deflected. If they had classical angular momentum, they could be oriented in any direction. And you would expect the beam to spread out into a continuous smear on the detector screen. But what Stern and Gerlach actually observed was that the beam split into two distinct spots. Two and only two. This meant the angular momentum was quantized. It could only point in two specific directions relative to the magnetic field, up or down, nothing in between. This was completely unexpected and completely at odds with classical physics. The silver atoms were behaving as if they had an angular momentum that could only take two values. And this angular momentum came from the outermost electron in the silver atom, which is spin 1/2. A spin 1/2 particle is strange in ways that are hard to visualize. Here is one of the strangest things about it. If you rotate a spin 1/2 particle by 360 degrees, it does not return to its original state. It picks up a negative sign on its wave function. You have to rotate it by 720 degrees, 2 full rotations, to get it back to exactly where it started. Nothing in our everyday experience works like this. If you rotate a book by 360 degrees, it is back to its original position. But a spin 1/2 particle needs twice that. This is a deep and fundamental difference between fermions and the objects we deal with in everyday life. And it connects directly to why their wave functions are antisymmetric. Let me now take you back to 1925, when this whole story really came together. The physics community was struggling with a serious problem. They had developed the early quantum theory. They understood that electrons in atoms could only occupy certain discrete energy levels. They had quantum numbers that described these levels. But there was something deeply puzzling. According to the theory as it stood, all the electrons in an atom should fall down to the lowest energy level. After all, systems tend to minimize their energy. If there were no rule preventing it, every electron would sit in the ground state. But this clearly was not happening in nature. Atoms had complex electron configurations. The periodic table had its elaborate structure of rows and columns. Different elements had different chemical properties. None of this would be possible if all electrons were in the same lowest state. Enter Wolfgang Pauli. He was an Austrian physicist known for his brilliant and sharp mind, and also for his sharp tongue. He was famous for dismissing bad physics with the cutting remark that it was not even wrong, meaning it was so vague it could not even be tested. In 1925, Pauli was studying the spectral lines of atoms. These are the specific wavelengths of light that atoms emit or absorb, and they serve as fingerprints of atomic structure. The patterns in these spectral lines were telling physicists something important about how electrons arranged themselves in atoms. And Pauli noticed something. To explain the observed patterns, he needed to assign 4 quantum numbers to each electron. 3 of these were already known. The principal quantum number, which described the energy level. The angular momentum quantum number, which described the shape of the orbital. And the magnetic quantum number, which described the orientation of the orbital in space. But these 3 were not enough. Pauli realized he needed a 4th quantum number, one that could only take 2 values. And his crucial insight was this: no 2 electrons in an atom could have the same set of all 4 quantum numbers. This was his exclusion principle. At the time Pauli proposed this, spin had not yet been formally identified. It was actually a few months later, in 1925, that George Uhlenbeck and Samuel Goudsmit proposed that Pauli's mysterious 4th quantum number corresponded to the intrinsic angular momentum of the electron, which they called spin. The electron could be spin up or spin down, giving 2 possible values for this 4th quantum number. And with all 4 quantum numbers, Pauli's rule made perfect sense. Each electron in an atom must have a unique address defined by its 4 quantum numbers. No 2 electrons can share the same address. It is like an incredibly strict apartment building. Every unit can only hold 1 tenant. If the unit is full, the next electron must find a different unit. Pauli received the Nobel Prize in Physics in 1945 for this discovery. But here is what is remarkable. Even Pauli himself was unsatisfied. He said he could not give a deeper logical reason why this principle existed. He could state it. He could prove it was consistent with quantum mechanics. Later, he would prove it had to be true given certain assumptions about quantum field theory. But the question of why nature chose to work this way, at the deepest level, remained open. And it remains open to this day. Let me now explain how this principle literally builds the atoms around us. This is one of the most beautiful stories in all of science. It is the story of how a single simple rule creates all the magnificent complexity of chemistry. Consider the hydrogen atom, the simplest atom in the universe. It has 1 proton and 1 electron. That electron sits in the lowest energy level available to it, the ground state. It has a principal quantum number of 1, an angular momentum quantum number of 0, a magnetic quantum number of 0, and it can be either spin up or spin down. Let us say it is spin up. Simple. Now consider helium. It has 2 protons, 2 neutrons, and 2 electrons. The first electron goes to the same ground state as in hydrogen. Spin up. The second electron also goes to the ground state, but it must take spin down, because spin up is already occupied. Both electrons are in the lowest possible energy level, but with opposite spins. The ground state is now completely full. There is no room for any more electrons there. Now here is the critical moment. Consider lithium, with 3 electrons. The first 2 fill up the ground state, just like helium. But the third electron cannot join them. Both available spots in the lowest energy level are taken. 1 spin up, 1 spin down. There is no room. So the third electron must go to the next energy level up. It is forced to occupy a higher energy state. And this is the beginning of atomic shell structure. This is why atoms have layers. This is why the periodic table is not just one element repeated over and over. Each new electron that gets added to an atom must find its own unique quantum state. And as the lower states fill up, electrons are forced into higher and higher energy levels, creating the rich and complex electronic structures that give each element its unique chemical personality. Think about what this means. The reason carbon behaves differently from nitrogen, which behaves differently from oxygen, which behaves differently from iron, all comes down to how many electrons each atom has, and how those electrons are arranged in their energy levels. And that arrangement is entirely dictated by the Pauli Exclusion Principle. Without this rule, all electrons would pile into the ground state, and every element would have essentially the same electronic structure. There would be no chemistry, no chemical bonds, no molecules, no water, no proteins, no life. The entire complexity of the material world. Everything you can see and touch and taste exists because electrons refuse to share quantum states. Let us go deeper into the structure of the periodic table. The table is arranged in rows and columns. Each row corresponds to filling up a new energy level. The first row has two elements, hydrogen and helium, because the first energy level can hold exactly two electrons. One spin up and one spin down. The second row has 8 elements, from lithium to neon, because the second energy level has more available quantum states. It has one sublevel with 2 spots and another sublevel with 6 spots, giving 8 total. The third row also has 8 elements for similar reasons. And as you go further down the table, the rows get longer because higher energy levels have even more available quantum states. The fourth row has 18 elements, because now you also start filling a sublevel with 10 available spots. And the pattern continues. The columns of the periodic table group elements with similar chemical properties together. The noble gases, helium, neon, argon, krypton, xenon, and radon, are all in the rightmost column. They all have completely filled outer electron shells. There are no empty slots for electrons to enter, and no weakly held electrons available to leave. This is why noble gases are chemically inert. They do not easily react with other elements. They are satisfied. Complete, on the other extreme, the elements in the leftmost column, the alkali metals like lithium, sodium, and potassium, all have a single electron in their outermost shell. This electron is relatively easy to remove, which makes these elements extremely reactive. They desperately want to give away that lonely outer electron. All of this structure, all of these chemical properties, everything that makes chemistry work, traces back to one rule. No 2 electrons in the same atom can have the same 4 quantum numbers. Now I want to take this story to a completely different scale. Let us leave atoms behind and travel to the stars. Because the Pauli Exclusion Principle does not just build atoms, it also determines how stars live and how they die. And the story is absolutely magnificent. A star like our Sun is a balance between 2 opposing forces. Gravity wants to crush the star inward. It wants to compress all that mass into the smallest possible volume. Working against gravity is the outward pressure generated by nuclear fusion in the star's core. The fusion reactions produce enormous amounts of energy, which heats the gas and creates an outward pressure that supports the star against gravitational collapse. This balance, called hydrostatic equilibrium, keeps the star stable for billions of years. Our Sun has been in this balanced state for about 4.5 billion years, and will continue for another 5 billion or so. But eventually, every star runs out of fuel. When the hydrogen in the core is used up, fusion slows down and eventually stops. Without the energy from fusion creating outward pressure, gravity starts winning. The star begins to collapse inward. Now, for a star like our Sun, something remarkable happens during this collapse. As the matter gets compressed more and more tightly, the electrons are forced into smaller and smaller regions of space. And here is where the Pauli Exclusion Principle comes in. As the electrons are squeezed together, they start to run out of available quantum states. The lower energy states are all full. The electrons are forced into higher and higher energy states, moving faster and faster. This creates a pressure, called electron degeneracy pressure that resists further compression. This pressure has nothing to do with temperature. It is not a thermal effect. It is purely a quantum mechanical effect arising from the fact that electrons are fermions and cannot share quantum states. For a star with a mass below about 1.4 times the mass of our Sun, this electron degeneracy pressure is strong enough to halt the gravitational collapse. The star reaches a new equilibrium as a white dwarf. A white dwarf is an incredibly dense object, roughly the size of Earth, but with the mass of a star. A teaspoon of white dwarf material would weigh about 15 tons on Earth. And this object is being held up against gravity not by any kind of nuclear burning, not by heat, but purely by the refusal of electrons to share quantum states. The Pauli Exclusion Principle is literally holding up a star. Let that sink in for a moment. The limit of 1.4 solar masses was calculated by a young Indian physicist named Subramanian Chandrasekhar in 1930 when he was just 19 years old on a ship traveling from India to England. This is called the Chandrasekhar limit, and it earned him the Nobel Prize in Physics in 1983. His calculation showed that if a white dwarf has more mass than this limit, the gravitational force is so strong that even electron degeneracy pressure cannot hold it up. The electrons are pushed to such high energies that something dramatic happens. They start combining with the protons in the atomic nuclei through a process called inverse beta decay. An electron merges with a proton to produce a neutron and a neutrino. The neutrinos escape, and you are left with a collapsing mass of neutrons. Now the neutrons, being fermions themselves, also obey the Pauli Exclusion Principle. As the collapse continues, the neutrons get squeezed together and they start running out of available quantum states, just like the electrons did before. This creates neutron degeneracy pressure, which is much stronger than electron degeneracy pressure because neutrons are much more massive than electrons. This neutron degeneracy pressure can halt the collapse of objects up to about 2 to 3 solar masses. The result is a neutron star. A neutron star is one of the most extreme objects in the known universe. It packs about 1.5 to 2 solar masses into a sphere only about 20 kilometers across. The density is absolutely staggering. A teaspoon of neutron star material would weigh about 6 billion tons. The surface gravity is about 200 billion times stronger than the gravity on Earth. If you dropped a marshmallow onto a neutron star, it would hit the surface with the energy of a nuclear bomb. Neutron stars also spin incredibly fast. Some neutron stars, called pulsars, rotate hundreds of times per second. They emit beams of electromagnetic radiation from their magnetic poles, and if those beams happen to sweep past Earth, we detect regular pulses of radio waves. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and the signals were so regular that for a brief time, the researchers considered the possibility that they might be artificial signals from an alien civilization. They even playfully named the source LGM-1, standing for Little Green Men, but it turned out to be a rapidly spinning neutron star, held up by the same quantum mechanical principle that determines the structure of atoms. But what happens if the collapsing mass is too great even for neutron degeneracy pressure to resist? If the remnant mass exceeds about 2 to 3 solar masses, even neutrons cannot hold up against gravity. The collapse continues, and nothing in known physics can stop it. The result is a black hole, an object so dense that its gravitational pull does not even allow light to escape. The formation of a black hole represents the ultimate failure of the Pauli Exclusion Principle to resist gravity. It is a case where gravity simply overwhelms the quantum mechanical resistance of fermions. What happens to matter inside a black hole is one of the great unsolved mysteries of physics. So let us step back and appreciate the full picture. The Pauli Exclusion Principle builds atoms by forcing electrons into different energy levels. It creates the periodic table. It makes chemistry possible. It gives matter its volume and structure. And then, on the grandest scales, it holds up white dwarf stars and neutron stars against the crushing force of gravity. One simple rule: no two fermions in the same state, operating at scales from smaller than an atom to larger than a star. The range and power of this principle is absolutely breathtaking. Now let me take you into a thought experiment that I think will really drive home how fundamental this rule is. Imagine you could flip a switch and turn off the Pauli Exclusion Principle. What would happen to the universe? The answer is total and immediate catastrophe. The very first thing that would happen is that every electron in every atom in the universe would instantly cascade down to the lowest energy level. Remember, electrons are in higher energy levels only because the lower levels are full. Remove the rule that fills them up, and there is no reason for any electron to be anywhere other than the ground state. When all electrons collapse to the ground state, atoms shrink dramatically. The size of an atom is determined by how far out its highest energy electrons extend. If all electrons are in the ground state, every atom becomes roughly the same incredibly tiny size. The differences between elements vanish. There are no electron shells. There is no reason for one element to behave differently from another chemically. All chemical bonds are based on the sharing or transfer of electrons between atoms that have specific electronic structures. If those structures disappear, bonds disappear. No bonds means no molecules, no water, no oxygen gas, no proteins, no DNA. Nothing that we associate with matter and life. Your body would simply cease to exist as a coherent structure. Every atom in it would shrink to a point-like state. The entire Earth, the Sun, the stars, everything would collapse into incredibly dense configurations. The universe would become an unrecognizable soup of ultra-dense matter. This thought experiment shows us something profound. The Pauli Exclusion Principle is not just some obscure rule of quantum physics that only matters in exotic situations. It is the reason matter has structure. It is the reason you have a body. It is the reason there are planets and stars and galaxies. It is arguably the single most important rule for the existence of complex structures in the universe. Without it, the universe would still exist, but it would be unimaginably simpler and completely devoid of anything we would recognize as structure or complexity. Now, I want to address a question that I think is really profound. What actually happens when you try to push two fermions into the same state? Is there a force that pushes them apart? This is a really important point and a common source of confusion. The answer is no. There is no force. The Pauli Exclusion Principle is not a force. It is not like electromagnetism, which pushes like charges apart through the exchange of photons. It is not like gravity, which pulls masses together through the curvature of space-time. It is something fundamentally different. It is a constraint on what states are even possible in nature. It is more like a rule of existence than a force of interaction. When we say fermions cannot occupy the same state, we do not mean there is some barrier preventing them from getting there. We mean that the state where two fermions have identical quantum numbers simply does not exist in the mathematical framework of quantum mechanics. The wave function for that state is exactly zero. It is not that the probability is very small. It is not that it is hard to achieve. It is that the mathematical description of that state is zero, meaning it has no physical reality. It is like asking what is north of the North Pole. The question does not have an answer because it does not even make sense within the framework. The state does not exist. However, there is something that looks like a force when you try to compress fermions together. If you try to squeeze a gas of electrons into a smaller and smaller volume, you will encounter resistance. This resistance is the degeneracy pressure we discussed earlier. It takes the form of a pressure, like a force per unit area. But its origin is purely quantum mechanical and purely a consequence of the exclusion principle. As you compress the gas, electrons are forced into higher momentum states because the lower states are full. Higher momentum means the electrons are moving faster, which means they are hitting the walls of the container harder and more frequently. This manifests as an outward pressure. So while the exclusion principle itself is not a force, it gives rise to effects that look very much like forces in certain situations. This is a subtle but important distinction. Let me now take you into an area that connects the Pauli exclusion principle to one of the deepest questions in physics. Why is it that particles with half-integer spin are fermions, while particles with integer spin are bosons? Why does spin determine statistical behavior? This connection is formalized in the Spin-Statistics Theorem, first proven rigorously by Wolfgang Pauli himself in 1940. It is also connected to work by Marcus Fiers from 1939. The theorem states that any consistent quantum field theory that respects special relativity must have half-integer spin particles that are fermions and integer spin particles that are bosons. You cannot have it any other way without violating fundamental principles like causality or the requirement that energy must be positive. The proof of this theorem is technical and relies on the mathematical framework of quantum field theory. But let me try to convey the essential ideas in an accessible way. In quantum field theory, particles are not fundamental objects. They are excitations of quantum fields that permeate all of space. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. Each type of particle corresponds to a different quantum field. Now, when you construct a quantum field theory, you need to make certain choices about how the field operators relate to each other. Specifically, you need to decide whether field operators at different points in space commute or anti-commute. Commuting means the order does not matter. Anti-commuting means swapping the order introduces a minus sign. For the theory to be consistent with special relativity, particularly with the requirement of causality, which says that events outside each other's light cones cannot influence each other, you are forced to make specific choices depending on the spin of the field. For integer spin fields, consistency requires commutation relations. This leads to Bose-Einstein statistics. For half-integer spin fields, consistency requires anti-commutation relations. This leads to Fermi-Dirac statistics and the Pauli exclusion principle. If you try to do it the other way around, if you try to quantize a spin 1/2 field with commutation relations, you get a theory where energy can be arbitrarily negative. Particles could have negative energy, which would make the vacuum unstable. The universe would immediately decay into a state of infinite negative energy. That obviously does not happen, so the theory would be inconsistent with reality. Similarly, if you try to quantize a spin 1 field with anti-commutation relations, you get violations of causality. Events could influence each other faster than light, again, inconsistent with reality. So the Spin-Statistics Theorem tells us that the connection between spin and statistics is not arbitrary. It is demanded by the deepest principles of physics. Relativity and quantum mechanics together force fermions to obey the exclusion principle. But even knowing this, there remains a question that I think is deeply unsatisfying for our intuitive understanding. Why is it that half-integer spin particles need anti-commutation relations for consistency? What is it about having spin 1/2 that makes a particle fundamentally incompatible with symmetric wave functions? The mathematical proof shows it must be so, but it does not give us a simple picture we can hold in our minds. Richard Feynman addressed this in his famous Feynman lectures on physics. He said, and I am paraphrasing here, that he had tried and failed to find a simple explanation for why spin and statistics are connected. he could not reduce it to something more basic. He seemed to regard it as one of those brute facts about nature that may not have a deeper explanation, or if it does, we have not found it yet. This is a humbling moment in physics. One of the most important rules governing the behavior of matter, and even the greatest minds cannot tell you why it is true in a way that feels intuitively satisfying. They can only show you that it must be true for the universe to be consistent. There is, however, a beautiful geometric way to think about why Fermion wave functions are antisymmetric that involves topology. This gets a bit abstract, but stay with me because it is genuinely elegant. Consider two identical particles in space. Now imagine swapping them. You take particle A to where particle B was, and particle B to where particle A was. You can think of this swap as a continuous process where the particles trace out paths in space as they exchange positions. Now, there are different topologically distinct ways to perform this swap. You can swap them by moving them around each other clockwise or counterclockwise. In three-dimensional space, it turns out that all these different swap paths are topologically equivalent. They can all be smoothly deformed into each other. And there are only two topologically distinct classes of paths when you consider what happens after two consecutive swaps. Two swaps can either be smoothly shrunk to no motion at all, which gives you bosons, or two swaps are topologically equivalent to one particle going around the other, which gives you fermions. This topological perspective actually leads to something fascinating. In 3 dimensions, there are only 2 possibilities, bosons and fermions. But in 2 dimensions, the topology is different. In 2 dimensions, you cannot move one particle over or under the other. The paths of particle exchange have a richer topological structure. 2 consecutive swaps can wind around each other multiple times, and each number of windings is topologically distinct. This means that in 2 dimensions, you can have particles that are neither fermions nor bosons. They are called anyons. When you swap 2 anyons, the wave function picks up a phase that is neither +1 nor -1, but some intermediate value. Anyons are not just theoretical curiosities. They appear to exist in certain 2-dimensional systems, like the fractional quantum Hall effect, where electrons confine to a thin layer in a strong magnetic field form exotic states of matter. Anyons are also incredibly important for the future of technology. Certain types of anyons, called non-abelian anyons, have the remarkable property that swapping them changes the quantum state of the system in a way that depends on the order in which swaps are performed. This makes them potentially useful for quantum computing. A quantum computer based on non-abelian anyons would be topological, meaning its computations would be protected from errors by the topology of the anyon braiding patterns. This is an active area of research, and if successful, it could lead to quantum computers that are inherently resistant to the noise and decoherence that plague current quantum computing approaches. So the same deep principles of particle exchange that give us the Pauli Exclusion Principle might also give us the quantum computers of the future. Let me now talk about what happens when fermions find a way around the exclusion principle. Because it turns out that in certain very special circumstances, fermions can effectively become bosons. This happens through a phenomenon called Cooper pairing, and it is at the heart of superconductivity. In a superconductor, electrons, which are fermions, form pairs. These pairs are called Cooper pairs, named after Leon Cooper, who described them theoretically in 1956. Now, a pair of fermions, each with spin 1/2, can combine to have a total spin of 0 or 1. If the total spin is 0, the pair behaves as a composite boson, and bosons do not obey the Pauli Exclusion Principle. Bosons can all pile into the same quantum state. When a large number of Cooper pairs all occupy the same quantum state, they form what is called a condensate. This condensate of paired electrons can flow through a material without any resistance at all. Zero electrical resistance. This is superconductivity. Superconductivity was first discovered by Heike Kamerlingh-Onnes in 1911 when he cooled mercury to extremely low temperatures and found that its electrical resistance suddenly dropped to zero. For decades, this phenomenon defied theoretical explanation. It was not until 1957 that John Bardeen, Leon Cooper, and John Robert Schrieffer published their theory, now known as BC's theory, which explained superconductivity in terms of Cooper pair formation. They received the Nobel Prize in Physics in 1972 for this work. The key insight is that the Pauli Exclusion Principle applies to individual electrons, not to pairs of electrons that form composite bosons. By pairing up, electrons find a loophole in the exclusion principle. They do not violate it, because the individual electrons in a Cooper pair still have different quantum numbers. But the pair as a whole entity can occupy the same state as other pairs, because the pair is a boson. It is a beautiful example of how nature finds creative solutions within its own rules. A similar phenomenon occurs with atoms. Helium has two stable isotopes, helium-4 with 2 protons and 2 neutrons, and helium-3 with 2 protons and 1 neutron. Helium-4 has an even number of fermions in its nucleus, making the atom as a whole a boson. Helium-3 has an odd number of fermions, making the atom as a whole a fermion. When you cool helium-4 below about 2.2 Kelvin, it becomes a superfluid. It can flow without any viscosity at all. It will creep up the walls of a container. It will pass through incredibly tiny holes that normal fluids cannot penetrate. This superfluidity occurs because the helium-4 atoms, being bosons, can all condense into the same quantum state, forming a Bose-Einstein condensate. Helium-3, on the other hand, being a fermion, cannot do this directly. The exclusion principle prevents the atoms from all occupying the same state. But in 1972, Douglas Osheroff, Robert Richardson, and David Lee discovered that helium-3 also becomes a superfluid, but at a much lower temperature, below about 2.5 millikelvin. The mechanism is the same as in superconductivity. The helium-3 atoms form pairs, analogous to Cooper pairs, and these pairs behave as composite bosons that can condense into the same state. This discovery earned them the Nobel Prize in Physics in 1996. Once again, fermions find a way around the exclusion principle by teaming up. Now let me take you into nuclear physics, because the Pauli Exclusion Principle plays an equally crucial role inside the atomic nucleus. Protons and neutrons, the particles that make up the nucleus, are both fermions with spin 1/2. They obey the exclusion principle just like electrons do. This means that protons in a nucleus cannot all be in the same state, and neither can neutrons. The result is a shell structure inside the nucleus, very similar to the electron shell structure in atoms. Nuclear physicists discovered that nuclei with certain specific numbers of protons or neutrons are exceptionally stable. These special numbers are 2, 8, 20, 28, 50, 82, and 126. They are called magic numbers. Nuclei with magic numbers of protons or neutrons are more tightly bound, more abundant in nature, and more resistant to radioactive decay. If both the proton number and the neutron number are magic, the nucleus is called doubly magic and is especially stable. Examples include helium-4 with 2 protons and 2 neutrons, oxygen-16 with 8 of each, calcium-40 with 20 of each, and lead-208 with 82 protons and 126 neutrons. The explanation for magic numbers comes from the nuclear shell model. developed in 1949 independently by Maria Goeppert-Mayer and by J. Hans D. Jensen, just as electron shells fill up according to the Pauli Exclusion Principle. Proton and neutron shells in the nucleus fill up the same way. When a shell is completely full, the nucleus is in a particularly stable configuration, just as atoms with full electron shells are particularly stable. Goeppert-Mayer and Jensen shared the Nobel Prize in Physics in 1963 for this insight. It is remarkable that the same principle operates at such different scales, governing both the arrangement of electrons around the nucleus and the arrangement of protons and neutrons within the nucleus. Let me talk about another fascinating consequence of the Pauli Exclusion Principle that might surprise you. It is directly responsible for the stability of matter itself. In 1967, Freeman Dyson and Andrew Leonard proved a theorem that showed that if electrons did not obey the Pauli Exclusion Principle, matter would not be stable. Specifically, they showed that the ground state energy of a collection of charged particles with Fermion statistics grows proportionally to the number of particles. This is what we mean by stability. If you double the amount of matter, you roughly double the energy. This is sensible and normal. But if you replace the Fermion statistics with boson statistics, the ground state energy grows much faster, proportionally to the number of particles raised to the power of 7/3 or even higher. This means that large collections of bosonic charged matter would have enormously negative ground state energies. They would collapse catastrophically. Two such objects brought together would release an explosive amount of energy. Dyson actually calculated that if electrons were bosons, bringing together a piece of matter roughly the size of your hand would release energy equivalent to a nuclear bomb. Every time you put two objects in contact, they would explode. This is not some gradual effect, it is catastrophic. The reason this does not happen in our universe is precisely because electrons are fermions. The Pauli Exclusion Principle prevents electrons from all collapsing into the lowest energy state, which keeps atoms at a reasonable size and prevents this catastrophic release of energy when atoms come together. So the stability of matter, the fact that you can pick up a glass of water without triggering a nuclear explosion, is directly due to the exclusion principle. Let us now talk about how the Pauli Exclusion Principle manifests in the technology we use every day. The most important example is semiconductor technology, which is the foundation of all modern electronics. Computers, smartphones, televisions, cars, medical equipment, virtually everything electronic in the modern world is based on semiconductors. And semiconductor physics is entirely dependent on the band structure of electrons in solids, which is a direct consequence of the Pauli Exclusion Principle. When atoms come together to form a solid, their electron energy levels split and spread out into bands. This happens because each atom's electrons interact with the electrons of neighboring atoms. And the Pauli Exclusion Principle requires that every electron must have a unique quantum state. With billions of atoms in a solid, the energy levels become so close together that they form continuous bands. Between these bands, there can be gaps, called band gaps, where no electron states exist. The key distinction between metals, semiconductors, and insulators comes down to how these bands are filled and how large the gaps between them are. In a metal, the highest occupied band is only partially filled. Electrons near the top of this band can easily move into empty states just above them, which means they can carry electrical current freely. This is why metals are good conductors. In an insulator, the highest occupied band is completely full, and there is a large gap before the next available band. Electrons cannot easily jump across this gap, so they cannot carry current. The material does not conduct electricity. A semiconductor is between these two extremes. It has a full band with a relatively small gap before the next band. At very low temperatures, a semiconductor acts like an insulator. But at room temperature, or with the addition of small amounts of impurity atoms called dopants, some electrons can gain enough energy to jump across the gap into the next band, allowing the material to conduct electricity. The entire operation of transistors, the building blocks of all digital electronics, depends on the ability to control which bands are filled and how easily electrons can jump between bands. This is only possible because of the Pauli Exclusion Principle, forcing electrons to fill up energy levels from the bottom. Without this principle, there would be no band structure, no band gaps, no semiconductors, and no electronics. Every computer, every phone, every digital device you have ever used owes its existence to the exclusion principle. Magnetic resonance imaging, or MRI, is another technology that depends on quantum spin and the exclusion principle. MRI works by exploiting the fact that protons in the nuclei of hydrogen atoms, which are abundant in the human body because of all the water we contain, have spin 1/2. When placed in a strong magnetic field, these proton spins align either with or against the field. The small energy difference between these two orientations can be detected using radio waves. By carefully controlling and measuring these spin orientations, MRI can build detailed, three-dimensional images of the inside of the body. This technology would not exist without the quantum mechanical spin that underlies the entire Fermion boson classification. Lasers also connect to the exclusion principle, although in a somewhat different way. A laser works by stimulated emission, where an excited atom emits a photon that is identical to a passing photon. Photons are bosons, so they are perfectly happy to be in the same state. In fact, they preferentially enter the same state. This is what makes laser light so special. All the photons have the same frequency, same direction, same phase. They are all in exactly the same quantum state. This is only possible because photons are bosons and do not obey the exclusion principle. If photons were fermions, you could never have two photons in the same state, and lasers would be impossible. So here the exclusion principle works by contrast. It explains why electrons create complex atomic structures with specific energy levels, and those energy levels allow stimulated emission to occur with photons, which being bosons, can all pile into the same state to create coherent laser light. Let me now discuss something that I find philosophically fascinating about the Pauli Exclusion Principle. It is the question of what it tells us about the nature of identity and individuality in the physical world. In our everyday experience, every object has an individual identity. Every person is unique. Every grain of sand is slightly different from every other grain of sand. We live in a world of distinguishable things. But at the quantum level, this notion of individuality completely breaks down. Two electrons are not just similar, they are identical in a way that has no parallel in our everyday experience. If you swap them, the universe does not change. They have no individuality, they have no identity markers. And yet, the Pauli Exclusion Principle says they cannot be in the same state. This creates a tension. If the electrons have no individual identity, what does it mean to say that two of them cannot be in the same state? After all, if they are truly identical, how do you even count them? How do you say there are two electrons here rather than one electron counted twice? The answer lies in the mathematical structure of quantum mechanics. The wave function for a system of identical fermions automatically encodes the information about how many particles are present, even without assigning individual identities to each one. The antisymmetry of the wave function naturally prevents the same state from being occupied more than once, without ever needing to label or identify individual particles. This has led some philosophers of physics to argue that quantum particles do not have identity in the traditional sense. They are not individuals. They are more like quantized excitations of a field. The electron field can be excited once, twice, 3 times in a given region, but it cannot have 2 excitations in exactly the same state. This view meshes well with quantum field theory, where particles are indeed treated as excitations of underlying fields rather than as fundamental objects with inherent identities. Now let me take you through the connection between the Pauli Exclusion Principle and one of the most exciting frontiers in modern physics: quantum computing. Quantum computers exploit the principles of quantum mechanics to perform certain computations exponentially faster than classical computers. They use quantum bits, or qubits, which, unlike classical bits that can only be 0 or 1, can exist in superpositions of both states simultaneously. The behavior of qubits is governed by quantum mechanical principles, and the distinction between fermions and bosons plays a role in how qubits are implemented and manipulated. One of the most promising approaches to quantum computing is topological quantum computing, which I mentioned earlier in connection with anyons. The idea is to encode quantum information in the topological properties of anyon world lines. Because these properties are topological, they are robust against local perturbations and noise. The quantum information is protected by the topology of the system, making it inherently more resistant to errors than other quantum computing approaches. Microsoft and other research groups have been actively pursuing this approach, attempting to create and manipulate non-abelian anyons in special materials and systems. The underlying physics is deeply connected to the spin-statistics connection and the behavior of particles under exchange, which is the same physics that gives us the Pauli Exclusion Principle. Another connection between the exclusion principle and quantum computing involves the use of fermions directly as qubits. In semiconductor-based quantum dots, individual electrons can be trapped and their spin states used as qubits. The spin-up and spin-down states of an electron naturally form a 2-level system that can serve as a qubit. The Pauli Exclusion Principle plays a role in ensuring that the electronic structure of the quantum dot is well defined, and that individual electrons can be isolated and controlled. It also helps protect the information stored in these spin qubits from certain types of decoherence. 2. Let me now discuss the role of the Pauli Exclusion Principle in one of the most spectacular events in the universe: a supernova. When a massive star exhausts its nuclear fuel, its core collapses. If the core mass is above the Chandrasekhar limit, electron degeneracy pressure cannot stop the collapse. The electrons are forced to combine with protons, producing neutrons and neutrinos. This process is called neutronization, and it releases an enormous flood of neutrinos. The core collapses down to a neutron star in a fraction of a second. But the outer layers of the star, which were supported by the core, suddenly have nothing beneath them. They fall inward at a significant fraction of the speed of light. When these infalling outer layers hit the incredibly dense, incompressible surface of the newborn neutron star, they bounce. This bounce, combined with the enormous energy deposited by the flood of neutrinos, drives a powerful shockwave outward through the star. This is the supernova explosion. It is one of the most energetic events in the universe, briefly outshining an entire galaxy of hundreds of billions of stars. And at its heart, the reason the neutron star surface is so incredibly rigid, the reason the infalling material bounces rather than just continuing to collapse, is neutron degeneracy pressure. The Pauli Exclusion Principle for neutrons creates a surface so stiff that nothing can compress it further. And that stiffness is what powers the supernova explosion. The elements created in this explosion are scattered into space. Elements heavier than iron, things like gold, silver, platinum, uranium, are produced during the extreme conditions of the supernova and its aftermath. These elements eventually end up in gas clouds that form new stars and planets. The gold in your jewelry, the uranium in nuclear reactors, the iodine in your thyroid gland were all created in supernova explosions that were powered by the Pauli Exclusion Principle. Every heavy atom in your body was forged in a cosmic explosion driven by the refusal of fermions to share quantum states. We are literally made of star stuff. And that star stuff exists because of the exclusion principle. Now let me discuss something more about the physics of neutron stars that I find absolutely incredible. The matter inside a neutron star exists in states that we cannot reproduce in any laboratory on Earth. The density and pressure are so extreme that matter behaves in ways that challenge our understanding of physics. Near the surface, you have a solid crust made of nuclei arranged in a crystal lattice, with electrons flowing through them like in a metal. As you go deeper, the nuclei become more and more neutron-rich. The Pauli Exclusion Principle is working overtime here, forcing neutrons into higher and higher energy states as they are packed more and more tightly. Below the crust, the nuclei dissolve into a sea of free neutrons with a small fraction of protons and electrons. This is the outer core. The neutrons here may form a superfluid, flowing without viscosity, while the protons may form a superconductor. Remember, both superfluidity and superconductivity arise from fermion pairing, and the same mechanism can operate with neutrons and protons. There is evidence for neutron superfluidity from observations of how neutron stars cool down after they form, and from sudden speed-ups in pulsar rotation called glitches, which can be explained by the interaction between the superfluid interior and the solid crust. Even deeper, in the inner core of a neutron star, the density exceeds the density of normal nuclear matter. At these extreme densities, no one is entirely sure what happens. One possibility is that the neutrons and protons dissolve further into their constituent quarks, forming a quark-gluon plasma. Another possibility is that strange matter containing strange quarks might form. There might be exotic phases like color superconductivity, where quarks form pairs analogous to Cooper pairs, and the quarks become superconducting. All of these exotic phases involve fermions, quarks, obeying or circumventing the Pauli Exclusion Principle in novel ways. The interior of a neutron star is one of the most extreme laboratories in the universe for studying how fermions behave under unimaginable pressure. Let me take a moment to talk about something that might seem like a simple question, but actually has a profound answer. Why does matter have volume? Why do objects take up space? This sounds so basic that you might think it is obvious, but it is actually a deep question. The answer is the Pauli Exclusion Principle. Let me explain. Consider a single atom. Its nucleus is incredibly tiny, about 100,000 times smaller than the atom itself. Almost all the mass is in this tiny nucleus. The electrons are distributed in a much larger volume around the nucleus. But why? Why do the electrons spread out so much? The answer is partly due to the uncertainty principle, which says that confining a particle to a small region increases its momentum and thus its kinetic energy. So there is a cost to squeezing electrons too close to the nucleus. But this effect alone would make atoms much smaller than they actually are. The real reason atoms are as large as they are is because electrons must stack up into different energy levels due to the exclusion principle, and higher energy levels correspond to larger orbital sizes. Think about it this way. If you have an atom with 50 electrons, like tin, those 50 electrons cannot all sit in the lowest energy level closest to the nucleus. They are forced to occupy higher and higher energy levels, which extend further and further from the nucleus. The outermost electrons in a tin atom are at a much greater distance from the nucleus than the innermost electrons, and it is those outermost electrons that determine the size of the atom. So the atom is large because the Pauli Exclusion Principle forces electrons outward into higher levels. And when atoms come together to form solid objects, it is the outermost electron clouds that touch and repel each other, again due to the exclusion principle. This is why solid objects feel solid. This is why you do not fall through your chair. The chair's atoms and your atoms cannot interpenetrate because their outermost electron clouds overlap, and the electrons in those clouds cannot occupy the same states. The exclusion principle creates an effective repulsion that gives matter its apparent solidity. This is why I said at the beginning that the common explanation for why solid objects are solid is wrong. It has nothing to do with atoms being hard little balls. Atoms are mostly empty space. The solidity of matter is a quantum mechanical effect arising from the Pauli Exclusion Principle. It is one of the most counterintuitive facts about the physical world. The chair you are sitting on feels solid because of an abstract quantum mechanical rule about identical fermions and antisymmetric wave functions. The connection between this abstract mathematics and the tangible experience of sitting on a solid surface is one of the most beautiful bridges between theory and everyday reality in all of physics. Let me now circle back to something I mentioned earlier and explore it in much more depth. I said that the Spin-Statistics Theorem proves that the connection between spin and statistics is required by the combination of quantum mechanics and special relativity. Let me unpack this a bit more, because I think it is one of the most profound results in theoretical physics. Special relativity tells us that physics must look the same in all reference frames that are moving at constant velocity relative to each other. This is called Lorentz invariance. It also tells us that no information can travel faster than light. This means that two events that are space-like separated, meaning no light signal can travel between them, cannot influence each other. This is the principle of causality. Quantum field theory is the framework that combines quantum mechanics with special relativity. In quantum field theory, fields are spread out over all of space, and particles are excitations of these fields. The fields at different points in space can interact with each other. But causality requires that field measurements at space-like separated points should not interfere with each other. Technically, this means that the field operators at space-like separated points must either commute or anti-commute. Now here is the crucial point. If you construct a quantum field theory for a spin 1/2 particle and you choose to use commutation relations, you find that you cannot simultaneously satisfy several requirements: Lorentz invariance, positive energy, and causality. Something breaks. Specifically, if you insist on commutation relations for a spin 1/2 field, you either get states with negative energy or you get violations of causality, or both. The only way to have a consistent theory that satisfies all the requirements is to use anti-commutation relations for the spin 1/2 field. And anti-commutation relations are precisely what give you the Pauli Exclusion Principle. Similarly, for a spin 1 field, using anti-commutation relations leads to problems. The energy cannot be bounded from below, or the theory becomes trivially zero. You must use commutation relations, which give you Bose-Einstein statistics. So the deep reason the Pauli Exclusion Principle exists, as far as we currently understand it, is that it is required by the simultaneous demands of quantum mechanics, special relativity, causality, and the stability of the vacuum. If fermions did not obey the exclusion principle, the universe would be unstable in the most fundamental way possible. This is an incredibly deep and beautiful result. It says that three of the most fundamental aspects of our universe, quantum mechanics, special relativity, and the stability of matter, are not independent requirements. They are interconnected. You cannot have a stable, relativistic, quantum universe without the Pauli Exclusion Principle. It is not an optional extra. It is built into the deepest fabric of reality. Let me now discuss a fascinating experiment that demonstrates the reality of Fermion antisymmetry in the most direct way possible. In 2000, a group of physicists at the Brookhaven National Laboratory performed an experiment looking at correlations between pairs of protons produced in heavy ion collisions. When gold nuclei are smashed together at high energies, they produce enormous numbers of particles, including pairs of protons. By measuring the momenta and positions of these proton pairs, the physicists could study how the protons were correlated with each other. They found that when two protons were produced very close together in space, with very similar momenta, the probability of detecting both of them was suppressed. There was an anti-correlation. The closer the protons were to being in the same quantum state, the less likely they were to be found together. This is the Pauli Exclusion Principle in action, directly observed in the correlations between particles. The effect is sometimes called a Fermi hole, a suppression of probability when two identical fermions are near each other in phase space. In contrast, when the same experiment is done with identical bosons, like pairs of identical pions, the opposite effect is observed. Identical bosons tend to be found near each other. They cluster together. This is called bunching, or the Hanbury-Brown and Twiss effect, first observed with photons in 1956 by Robert Hanbury-Brown and Richard Twiss. Photons from a thermal source tend to arrive in pairs. They bunch together because their wave function is symmetric. This is the bosonic counterpart to the fermionic antibunching. It beautifully illustrates the fundamental difference between the two classes of particles. Fermions avoid each other. Bosons flock together. Speaking of experiments, let me tell you about one of the most remarkable experimental tests of the Pauli Exclusion Principle. Because the principle is so fundamental, physicists have wondered whether it is exactly true, or whether there might be tiny violations. What if the exclusion principle is almost perfectly obeyed, but there is a tiny probability that two fermions can occasionally share the same state? Several experiments have been designed to search for such violations. One approach is to look for anomalous X-rays from atoms. If an electron occasionally violates the exclusion principle and drops into an already full inner shell, it would emit an X-ray with a specific energy that is slightly different from the normal X-ray energies of that atom. Experiments have searched for these anomalous X-rays and found nothing, placing incredibly stringent limits on any possible violation. The probability of violation has been bounded to be less than about 1 part in 10 to the power of 29. That is an astonishingly small number. The exclusion principle appears to be exact, or if there is any violation, it is incredibly tiny. Another experiment, called VIP, which stands for Violation of the Pauli Exclusion Principle, was conducted at the Gran Sasso Underground Laboratory in Italy. It used a similar approach, circulating electric current through a copper strip and looking for anomalous X-rays that would indicate electrons violating the exclusion principle as they entered the copper atoms. The results again showed no violation with extremely high precision. As far as we can tell, the Pauli exclusion principle is perfectly, exactly obeyed by every fermion in the universe. Now I want to take you through an absolutely beautiful application of the Pauli exclusion principle that you might not have heard about before. It is called the Fermi gas model, and it gives us a powerful way to understand the behavior of large collections of fermions. Consider a gas of fermions, like the electron gas inside a metal. At zero temperature, you might expect all the electrons to have zero kinetic energy. In a classical gas, that is exactly what would happen. At absolute zero, all motion would stop. But for a Fermi gas, this is impossible because of the exclusion principle. All the electrons cannot be in the same zero-energy state. They must stack up into different energy levels, filling them from the bottom up. The result is that, even at absolute zero temperature, the electrons in a metal have a range of energies, from zero up to some maximum value called the Fermi energy. The Fermi energy depends on the density of electrons. For typical metals, it corresponds to electron speeds that are about 1% of the speed of light. Think about that. Even at absolute zero, when you would naively expect everything to be perfectly still, the electrons in a metal are zooming around at enormous speeds, purely because the Pauli Exclusion Principle forces them into higher and higher energy states. This has real, measurable consequences. It affects the heat capacity of metals, their electrical conductivity, their magnetic properties, and much more. The concept of a Fermi energy extends far beyond metals. It applies to any collection of fermions. In a white dwarf star, the electron Fermi energy determines the degeneracy pressure that supports the star. In a neutron star, the neutron Fermi energy is enormous because the neutrons are packed so densely. Even in the nucleus of a normal atom, the protons and neutrons have a Fermi energy that affects nuclear structure and nuclear reactions. The Fermi gas model is one of the most widely used tools in physics, applicable to systems ranging from metals to atoms to stars. Let me talk about another profound consequence of the exclusion principle that connects quantum physics to the large-scale structure of the universe. The existence and properties of main sequence stars like our Sun depend critically on the exclusion principle. Here is how. The core of the Sun is incredibly hot and dense. Under these conditions, the hydrogen nuclei, which are protons, are moving fast enough to overcome their electrostatic repulsion and get close enough for the strong nuclear force to grab them. This is nuclear fusion. Two protons fuse together, and through a series of reactions, 4 protons are eventually converted into one helium nucleus, releasing enormous energy. But the rate at which this fusion occurs depends on the temperature and density of the core. And the structure of the core, how hot and dense it is, depends on how the star balances gravity against pressure. The gas pressure in the core is determined by the ideal gas law plus quantum corrections. For low-mass stars, the electrons in the core are partially degenerate, meaning the Pauli Exclusion Principle is significantly affecting their behavior. This modifies the pressure-temperature relationship and thus the rate of nuclear burning. For very low-mass stars, near the boundary between stars and brown dwarfs, electron degeneracy is crucial in determining whether nuclear fusion can even be sustained. Moreover, as stars evolve and develop different layers, electron degeneracy often plays a role. In red giant stars, the core becomes degenerate while the outer layers expand enormously. This degenerate core heats up until it reaches the temperature for helium fusion, which then ignites in a dramatic event called the helium flash. The helium flash occurs precisely because the degenerate core does not expand when heated, unlike normal gas. Normally, if a region gets hotter, it expands, which cools it down, creating a stable negative feedback loop. But a degenerate gas does not work this way. Its pressure is determined by the exclusion principle, not by temperature. So it can heat up without expanding, leading to a runaway thermonuclear explosion inside the star. The helium flash releases enormous energy in seconds, but is absorbed by the outer layers, so we do not see it from outside the star. But it dramatically restructures the star's interior. Let me now discuss a question that sometimes confuses people. If the Pauli Exclusion Principle applies to all identical fermions, does it apply to fermions that are far apart? If there is an electron here on Earth and an electron in the Andromeda galaxy, are they somehow constrained by the exclusion principle? The answer is technically yes, but practically no. Here is why. The exclusion principle says that the combined wave function of all identical fermions in the universe must be antisymmetric. This applies regardless of distance. So in principle, every electron in the universe is entangled with every other electron through the requirement of antisymmetry. However, for particles that are very far apart, the overlap of their wave functions is essentially zero. The wave function of the electron here on Earth does not extend to the Andromeda galaxy in any meaningful sense. It has an exponentially small tail, so small that it has no measurable effect. So while the principle technically applies to all identical fermions everywhere, it only has practical consequences for fermions that are close enough for their wave functions to significantly overlap. In practice, this means fermions within the same atom, the same molecule, the same material, or the same region of a star. For fermions that are far apart, the exclusion principle is there in the formalism, but has no observable effect. This raises an interesting philosophical question, though. If the antisymmetry requirement is formally there for all electrons in the universe, does this mean all electrons are somehow fundamentally connected? Some physicists have argued that this suggests electrons are not really individual particles at all, but rather excitations of a single universal electron field. In quantum field theory, this is literally how things are described. There is one electron field permeating all of space, and what we call electrons are localized excitations of this field. The antisymmetry requirement is automatically built into the field, not imposed on individual particles after the fact. This perspective dissolves the puzzle. There is no need to imagine distant electrons communicating with each other about their quantum numbers. The field itself is constructed in a way that antisymmetry is a built-in feature. Let me now take a slight detour into something called exchange interaction, which is one of the most important practical consequences of the Pauli Exclusion Principle. Exchange interaction is not a fundamental force. It is not mediated by any particle. It is an apparent interaction that arises purely from the symmetry requirements of identical particle wave functions. And it is responsible for one of the most familiar phenomena in everyday life: magnetism. Here is how it works. Consider two electrons in a system, like two electrons in an atom or in neighboring atoms. The combined wave function must be antisymmetric. Now, the total wave function is a product of a spatial part and a spin part. For the total to be antisymmetric, either the spatial part is symmetric and the spin part is antisymmetric, or the spatial part is antisymmetric and the spin part is symmetric. The symmetric spin state is the one where both spins are aligned, both up or both down. This is called the triplet state. The antisymmetric spin state is where the spins are opposite. This is called the singlet state. Now, the spatial configuration of the electrons affects their electrostatic energy. If the spatial wave function is symmetric, the electrons tend to be closer together, which increases their electrostatic repulsion. If the spatial wave function is antisymmetric, the electrons tend to be further apart, reducing their repulsion. This means there is an energy difference between the triplet state, where spins are parallel, and the singlet state, where spins are antiparallel. This energy difference is called the exchange energy, and it acts as if there is a force aligning or anti-aligning the electron spins, but there is no actual spin-dependent force. The effect is entirely due to the Pauli Exclusion Principle, requiring the total wave function to be antisymmetric. In many materials, the exchange interaction favors parallel alignment of electron spins. This can lead to ferromagnetism, where large numbers of electron spins align in the same direction, creating a macroscopic magnetic field. Iron, nickel, and cobalt are ferromagnetic because of the exchange interaction between their electrons. Every refrigerator magnet, every compass needle, every electric motor is working because of the exchange interaction. which is a direct consequence of the Pauli Exclusion Principle. So next time you stick something to your refrigerator with a magnet, remember that the force holding it there ultimately traces back to the antisymmetry of Fermion wave functions. In other materials, the exchange interaction favors antiparallel alignment, leading to antiferromagnetism, where neighboring spins point in opposite directions. And in others, the situation is more complex, leading to exotic magnetic phenomena like spin glasses and frustrated magnets. The entire rich field of magnetism in condensed matter physics is built on the foundation of exchange interactions arising from the exclusion principle. Now I want to discuss how the Pauli Exclusion Principle relates to the periodic table in a bit more depth. Because the periodic table is one of the most elegant and information-rich organizational schemes in all of science, and it is entirely a product of this principle. Let us walk through the logic carefully. Each electron in an atom is described by 4 quantum numbers. The principal quantum number, which we call n, can take values 1, 2, 3, 4, and so on. It roughly corresponds to the energy and size of the orbital. The angular momentum quantum number, which we call L, can take values from 0 up to n-1. It describes the shape of the orbital. Orbitals with L equals 0 are spherical and called s orbitals. Orbitals with L equals 1 are dumbbell-shaped and called p orbitals. Orbitals with L equals 2 are more complex and called d orbitals. And orbitals with L equals 3 are called f orbitals. The magnetic quantum number, which we call L, can take values from negative L to positive L, giving 2L plus 1 possible values. It describes the orientation of the orbital in space. And finally, the spin quantum number, which we call MES, can be either plus 1/2 or minus 1/2, corresponding to spin up or spin down. The Pauli Exclusion Principle says no 2 electrons can have the same values for all 4 quantum numbers. This immediately tells us how many electrons each subshell can hold. An S subshell with L equals 0 has only one value of MEL, which is 0, and 2 values of MS, giving room for 2 electrons. A P subshell with L equals 1 has 3 values of ML, which are -1, 0, and +1, and 2 values of MS for each, giving room for 6 electrons. A D subshell can hold 10 electrons. An F subshell can hold 14 electrons. Now, as you go across a row of the periodic table, you are adding 1 electron at a time. Each new electron goes into the lowest available quantum state that is not already occupied. The first row of the periodic table fills the 1s subshell, which holds 2 electrons. So there are 2 elements in the first row, hydrogen and helium. The second row fills the 2s and 2p subshells, which hold 2 and 6 electrons respectively, for a total of 8. So there are 8 elements in the second row, from lithium to neon. The third row fills 3s and 3p, another 8 elements from sodium to argon. The fourth row starts filling 4s, then 3d, then 4p. The 3d subshell holds 10 elements, which are the transition metals from scandium to zinc. So the fourth row has 18 elements. The fifth row is similar, filling 5s, 4d and 5p. The sixth row is even longer because it also fills the 4if subshell, which holds 14 elements, the lanthanides. And the seventh row fills 5if, the actinides. Every aspect of this structure, the number of elements in each row, the grouping of elements with similar properties into columns, the existence of transition metals and rare earth elements. All of it comes directly from the Pauli Exclusion Principle, determining how many electrons each subshell can hold. Think about what happens at the noble gases. Helium has a full 1s shell. Neon has full 2s and 2p shells. Argon has full 3s and 3p shells. These completed shells are exceptionally stable configurations. Removing an electron from a noble gas requires a lot of energy, and adding an electron to one does not release energy. This is why noble gases are chemically inert. They do not form bonds easily because their electronic structure is already in its most stable possible configuration, thanks to the exclusion principle having filled every available state in the outer shell. Now consider what happens right after a noble gas. Sodium has one more electron than neon. That electron cannot fit into the neon core, all those states are full. It must go into the next available level, 3s. This single outer electron is loosely held and easily removed, making sodium a highly reactive alkali metal. The same pattern repeats with potassium, rubidium, cesium, and francium. All have one loosely held outer electron beyond a noble gas core. All are reactive alkali metals. The chemical similarity of elements in the same column of the periodic table, which Dmitri Mendeleev noticed empirically in 1869, long before quantum mechanics was developed, is completely explained by the shell structure that arises from the Pauli Exclusion Principle. Mendeleev arranged elements by atomic weight and noticed that properties repeated periodically. He even predicted the existence and properties of several elements that had not yet been discovered, based on gaps in his table. But he had no idea why the periodicity existed. It was not until quantum mechanics and the Pauli Exclusion Principle were developed in the 1920s that the explanation became clear. The periodicity exists because electron shells fill up and new shells begin. Over and over, each time creating elements whose outermost electrons are in similar configurations and thus have similar chemical properties. Let me now discuss another astounding consequence of the Pauli Exclusion Principle that appears in astrophysics. I have talked about white dwarfs and neutron stars, but there is another phenomenon called a Type 1a supernova that is directly connected to the Chandrasekhar limit, which is itself a consequence of the exclusion principle. A Type 1a supernova occurs when a white dwarf in a binary star system orbiting closely with a companion star accumulates matter from that companion. As the white dwarf gains mass, it approaches the Chandrasekhar limit of 1.4 solar masses. Near this limit, the star becomes unstable. What happens is that as the white dwarf approaches the limit, the electrons in its core are forced to such high energies that the star's temperature rises enough to ignite carbon fusion. But because the star is supported by degeneracy pressure, which does not depend on temperature, it does not expand in response to the increased heat. There is no safety valve. The fusion runs away, releasing enormous energy, and the entire star is blown apart in a thermonuclear explosion. Nothing remains. No neutron star, no black hole. The entire white dwarf is destroyed. Type 1a supernovae are extraordinarily important in astronomy because they all occur at roughly the same mass, the Chandrasekhar limit, which means they all release roughly the same amount of energy, which means they all have roughly the same peak brightness. This makes them standard candles, objects whose true brightness is known, allowing astronomers to measure distances to faraway galaxies by comparing the apparent brightness to the known true brightness. In 1998, two teams of astronomers used Type 1a supernovae to measure the distances to very remote galaxies and made one of the most stunning discoveries in the history of science. They found that the expansion of the universe is accelerating. The universe is not just expanding, it is expanding faster and faster. This led to the concept of dark energy, a mysterious form of energy that permeates all of space and drives this acceleration. Saul Perlmutter, Brian Schmidt, and Adam Riess received the Nobel Prize in Physics in 2011 for this discovery. And at the foundation of the entire measurement technique is the Chandrasekhar limit, which comes from the Pauli Exclusion Principle for electrons. So our knowledge that the universe's expansion is accelerating one of the most profound discoveries in modern cosmology, is built on a foundation that traces back to electrons refusing to share quantum states. The connections in physics are endlessly beautiful. Let me now talk about something called the Fermi surface, which is one of the most important concepts in solid-state physics. In a metal, the conduction electrons fill up energy states from the bottom, one by one, due to the Pauli Exclusion Principle. At absolute zero, there is a sharp boundary in energy between the filled states and the empty states. In momentum space, this boundary forms a surface called the Fermi surface. The shape of the Fermi surface depends on the crystal structure of the metal and the details of how electrons interact with the ions in the lattice. For a simple, idealized metal, the Fermi surface is just a sphere. But for real metals, it can take on incredibly complex and beautiful shapes. The Fermi surface determines almost all the electronic properties of a metal: the electrical conductivity, the thermal conductivity, the magnetic behavior, the response to electromagnetic waves, the behavior under high magnetic fields. All of these depend primarily on what is happening at or near the Fermi surface. Electrons deep below the Fermi surface are locked in place by the exclusion principle. They cannot participate in any processes because there are no available states for them to move into. Only electrons near the Fermi surface, where there are empty states available nearby in energy, can respond to external stimuli. This is why, even though a metal contains an enormous number of electrons, only a small fraction of them near the Fermi surface contribute to its electronic properties. Experimental techniques like de Haas-Van Alphen oscillations, cyclotron resonance, and angle-resolved photoemission spectroscopy allow physicists to map out the Fermi surface of materials in exquisite detail. The shapes they find are often stunningly complex and beautiful, and they encode all the information about how electrons are arranged in the material. Entire careers in condensed matter physics are built around understanding Fermi surfaces and what they tell us about materials. Now let me step back and address something about the exclusion principle that I think is deeply interesting from a conceptual standpoint. Throughout this discussion, I have been talking about the exclusion principle as a rule or a constraint. But what is it really? Is it a law of physics, like Newton's laws of motion? Is it a consequence of deeper laws, like the Spin-Statistics Theorem? Is it a principle, like the principle of relativity, or is it something else entirely? The honest answer is that it occupies a somewhat unusual place in the structure of physics. It is not a force. It is not a fundamental interaction. It is not an equation of motion. It is a constraint on the types of quantum states that can exist. It is a statement about the allowed states of a system rather than about how those states evolve in time. In the language of quantum field theory, it is built into the mathematical structure of the theory through the choice of anti-commutation relations for Fermion field operators. It is not imposed as a separate rule on top of the theory. It is woven into the very formulation of the theory. Some physicists have argued that the exclusion principle is actually more fundamental than the forces of nature. Forces can be modified, unified, or extended. We can imagine different forces, but the basic distinction between fermions and bosons seems to be incredibly fundamental to the mathematical structure of quantum field theory in ways that might not easily be changed. If you try to violate it, you do not just get a different universe. You get an inconsistent theory. The mathematics breaks down. You cannot even formulate a sensible theory without it. This suggests that the exclusion principle is not just a fact about our universe. It might be a logical necessity for any consistent quantum universe that respects relativity. Let me now discuss one more beautiful application of the Pauli exclusion principle that connects to everyday chemistry in a way that many people find surprising. It is the explanation for why certain molecules have the shapes they have, and why those shapes matter for their chemical and biological function. Consider water, a molecule made of 2 hydrogen atoms bonded to 1 oxygen atom. The oxygen atom has 8 electrons. 2 fill the first shell. The remaining 6 are in the second shell, which has room for 8. 6 out of 8 spots are filled. This means oxygen wants 2 more electrons to complete its shell. It gets them by sharing electrons with 2 hydrogen atoms, forming 2 covalent bonds. But why does the water molecule have a bent shape rather than being linear? The answer involves the arrangement of electron pairs around the oxygen atom. Oxygen has 4 pairs of electrons in its outer shell, 2 bonding pairs shared with hydrogen, and 2 lone pairs not shared with anything. These 4 pairs repel each other due to electrostatic repulsion between their negative charges, and they arrange themselves to be as far apart as possible. This gives a roughly tetrahedral arrangement, which results in a bent molecule with a bond angle of about 104.5 degrees. This shape has enormous consequences. Because the water molecule is bent, it has a permanent electric dipole moment. The oxygen end is slightly negative, and the hydrogen end is slightly positive. This polarity is why water is such an excellent solvent, why ice floats, why water has an unusually high boiling point, and why life as we know it depends on liquid water. And all of this traces back to how many electrons oxygen has, how many spots are available in its outer shell, and how those electron pairs arrange themselves. Every step of this logic is governed by the Pauli Exclusion Principle, determining how electrons fill shells. The same kind of reasoning explains the shapes of countless other molecules that are critical for biology. The double helix of DNA has its specific shape because of the hydrogen bonds between base pairs, which exist because of the specific electronic structures of the atoms involved, which are determined by the exclusion principle. Proteins fold into their functional shapes because of interactions between amino acids that have specific chemical properties, again determined by electronic structure and thus by the exclusion principle. The molecular machinery of life, from enzymes to receptors to ion channels, all depends on molecules having precisely the right shapes and chemical properties. And those shapes and properties all trace back to the quantum mechanical shell structure of atoms. I want to talk about one more astrophysical application before I bring this journey toward its conclusion. It involves something called a degenerate gas and its equation of state. In normal, non-degenerate gas, the relationship between pressure, density, and temperature is given by the ideal gas law. Pressure is proportional to density times temperature. If you heat the gas, the pressure goes up. If you compress it, the pressure goes up. This is how everyday gases behave. But a degenerate Fermi gas is completely different. When the fermions are packed so tightly that the Pauli Exclusion Principle dominates their behavior, the pressure is determined almost entirely by the density, not the temperature. Doubling the temperature of a degenerate gas barely changes its pressure at all. This has profound consequences for astrophysics. In a normal gas cloud, heating it up increases the pressure and causes it to expand. Cooling it down decreases the pressure and allows it to contract. This negative feedback keeps things stable. But in a degenerate gas, temperature and pressure are decoupled. You can heat it up without it expanding. You can cool it down without it contracting. This is why white dwarfs cool down gradually over billions of years without changing size. Their structure is supported by degeneracy pressure, which does not depend on temperature. So as they radiate energy and cool down, they just sit there getting dimmer and dimmer, eventually becoming cold, dark objects called black dwarfs. The universe is not old enough for any white dwarfs to have cooled completely to black dwarfs yet. But they will eventually, over trillions of years. These dark remnants will be among the last surviving structures in the far future of the universe. silent monuments to the Pauli Exclusion Principle that holds them up long after every star has burned out and every other source of light has faded. Let me now bring together several threads and discuss what I think is one of the most philosophically profound aspects of the Pauli Exclusion Principle. It is the idea that complexity in the universe arises from constraints, not from complexity in the underlying rules. The rules of quantum mechanics are incredibly simple. The Pauli Exclusion Principle can be stated in one sentence. No two identical fermions can occupy the same quantum state. That is it. One sentence. And yet, from this single constraint, combined with the electromagnetic force between charged particles, arises the entire periodic table, all of chemistry, all of molecular biology, all of material science, the structure of stars, the mechanism of supernovae, the existence of neutron stars, the technology of semiconductors and superconductors, the phenomenon of magnetism, and ultimately the existence of complex structures like planets, ecosystems, and thinking beings. This is a recurring theme in physics. Simple rules give rise to incredible complexity. The rules of chess are simple, but the game is infinitely rich. The rules of quantum mechanics are simple, but the universe they produce is infinitely complex. The Pauli Exclusion Principle is perhaps the single best example of this. It is one constraint, and it produces virtually all the structural complexity we see in the material world. Without it, the universe would be simple and uniform, a featureless soup of identical collapsed atoms. With it, the universe is rich, diverse, structured, complex, and capable of producing life and consciousness. One rule makes the difference between a boring universe and an interesting one. I find this deeply moving, not in a mystical or supernatural sense, but in a purely intellectual sense. The fact that the mathematical structure of quantum field theory necessarily produces this one constraint, which necessarily produces all this complexity, strikes me as one of the most beautiful things about the physical world. It suggests that the complexity we see around us is not an accident. It is not arbitrary. It is a necessary consequence of the deepest mathematical structure of reality. Given quantum mechanics and special relativity, you necessarily get fermions. Given fermions, you necessarily get the exclusion principle. Given the exclusion principle, you necessarily get atomic structure, chemistry, and all the rest. The complexity of the world is mathematically inevitable. Now, I want to talk about one more topic before I wrap up this exploration. It is the question of whether the Pauli Exclusion Principle could ever be violated under extreme conditions. Perhaps near the singularity of a black hole, or in the very early universe. This is actually a deep and somewhat controversial question. In standard physics, as I have discussed, the principle is exact. It cannot be violated even slightly without the entire mathematical framework becoming inconsistent. The experiments I mentioned earlier have confirmed this to extraordinary precision. However, some speculative theories beyond the standard model have considered the possibility of small violations. For instance, some approaches to quantum gravity, which attempt to unify quantum mechanics with general relativity, suggest that the structure of space-time itself might break down at the Planck scale, which is about 10 to the power of -35 meters. If space-time has some kind of discrete or foamy structure at this scale, it is conceivable that the spin-statistics connection might not hold exactly. These are extremely speculative ideas, and there is currently no experimental evidence for any violation. But the fact that physicists take the question seriously enough to design and run experiments searching for violations tells you how fundamental and important this principle is. Any confirmed violation, no matter how tiny, would revolutionize our understanding of physics. Let me also briefly discuss the historical context of the exclusion principle's discovery. because I think it illuminates how scientific progress actually works. In the early 1920s, atomic physics was in a state of productive confusion. The old quantum theory of Bohr and Sommerfeld could explain the hydrogen atom, but it struggled with heavier atoms. The spectral lines of multi-electron atoms were more complex than the theory predicted. There were anomalies, patterns that did not fit. Many physicists were working on this problem simultaneously. Edmund Stoner, a British physicist, made an important contribution in 1924 when he showed that the number of electrons in a completed shell could be understood if you assigned 3 quantum numbers to each electron. But it was Pauli who took the crucial additional step of proposing the 4th quantum number and the exclusion rule. Pauli was known for his incredible physical intuition combined with mathematical rigor. He was also known for his sharp critical faculty. He dismissed ideas he considered wrong with memorable put-downs. But when he was right, he was spectacularly right. And the exclusion principle is his greatest legacy. It is one of those discoveries that seems obvious in hindsight, but required tremendous insight to make at the time. It is worth noting that Pauli proposed the exclusion principle purely on empirical grounds, as a rule that made the observations make sense. The deeper justification, through the Spin-Statistics Theorem and quantum field theory, came more than a decade later. This is actually quite common in physics. Often the correct result is found first, and the deeper understanding of why it is correct comes later. Nature reveals its secrets, one layer at a time. Let me now bring this entire discussion together with a grand synthesis. We started with a simple question. Why does every fermion need permission to exist in the same place? And we have traveled an enormous distance to answer it. We have seen that the answer connects to the deepest levels of physics, quantum mechanics, special relativity, quantum field theory, topology. We have seen that the consequences spread across every scale in the universe, from the structure of individual atoms to the behavior of dying stars. We have seen that this one rule is responsible for the periodic table, for chemistry, for the properties of materials, for the stability of matter, for the support of white dwarfs and neutron stars, for the mechanism of supernovae, for the phenomenon of magnetism, for semiconductor electronics, for superconductivity, and ultimately for the existence of the complex structured universe we inhabit. The Pauli Exclusion Principle is not just a rule in physics, it is one of the fundamental organizing principles of reality. It takes the raw material of quantum fields and forces it into structured, complex, diverse configurations. Without it, the universe would be simple to the point of being trivial. With it, the universe is rich beyond imagining. And the most remarkable thing is that this principle is not imposed from outside. It is not an arbitrary rule chosen by some designer. It is a mathematical necessity, demanded by the internal consistency of quantum field theory combined with special relativity. The universe has no choice but to obey it. And because it obeys it, we exist. Every atom in your body right now has its electrons arranged in specific shells because of this principle. The oxygen you are breathing exists as a diatomic molecule because of this principle. The iron in your blood binds oxygen because of the specific electronic configuration of iron, which is determined by this principle. The neurons in your brain fire because of ion channels in their membranes, which work because of the specific shapes and chemical properties of protein molecules, which fold correctly because of interactions determined by electronic structure, which is governed by this principle. You are listening to or reading these words because a chain of causation stretching from the fundamental laws of quantum field theory all the way up through atoms and molecules and cells and neurons has produced a conscious being capable of understanding the universe. And at the bottom of that chain, holding everything up, is one simple rule. No two identical fermions can be in the same quantum state. The next time you sit in a chair, or pick up a cup, or feel the solidity of the ground beneath your feet, remember what is actually happening. You are not touching a solid surface. Your atoms are not in contact with the atoms of the chair or the cup or the ground. What is happening is that the electron clouds of your atoms and the electron clouds of those other atoms are overlapping, and the Pauli Exclusion Principle is preventing them from interpenetrating. An abstract quantum mechanical rule, operating at scales far too small to see or feel, is creating the experience of solidity and touch. The world you feel is a quantum mechanical illusion. But what a magnificent illusion it is. And think about the neutron star, spinning hundreds of times per second in the void of space, emitting beams of radiation that sweep across the cosmos. Inside it, neutrons are packed to unimaginable density, each one in its own unique quantum state, the exclusion principle preventing them from collapsing further. That neutron star is a monument to quantum mechanics, a place where the Pauli Exclusion Principle is operating at its most extreme, holding up a star mass of matter in a volume smaller than a city. If you could somehow turn off the exclusion principle, that neutron star would instantly collapse into a black hole. The principle is literally all that stands between that object and gravitational oblivion. Or think about the white dwarf remnant of a star like our Sun, billions of years in the future. Long after our Sun has exhausted its fuel and shed its outer layers, its core will remain as a white dwarf, slowly cooling over trillions of years. No nuclear reactions, no heat source, just a ball of degenerate matter, held up by the exclusion principle, gradually cooling toward absolute zero. It will still be there long after the last stars have burnt out, long after the universe has grown dark and cold, a silent, dark remnant, still held up by the refusal of electrons to share quantum states. The Pauli Exclusion Principle is eternal. As long as the laws of physics hold, it will continue to shape the universe, from its smallest components to its largest structures. I want to leave you with one final thought. We have covered an enormous amount of ground today. We have gone from quantum mechanics to stellar astrophysics to philosophy to technology. And all of it was connected by one thread: the antisymmetric nature of Fermion wave functions. This one mathematical property, that swapping two identical fermions introduces a minus sign, has consequences that span the entire universe. It is one of those rare scientific facts that is simultaneously simple enough to state in one sentence and profound enough to spend a lifetime exploring its consequences. Physics is full of such simple rules with vast consequences. Newton's law of gravity is one equation, but it explains the motions of all the planets, the tides, the trajectories of spacecraft. Maxwell's equations are just 4 equations, but they describe all of electromagnetism, light, radio waves, and every electromagnetic phenomenon. And the antisymmetry of Fermion wave functions is just one property, but it explains the structure of atoms, the periodic table, chemistry, the properties of materials, the stability of matter, the structure of stars, and the existence of complex organized structures in the universe. This is what physics is about. It is about finding the simple rules beneath the apparent complexity of the world. And the Pauli Exclusion Principle is one of the most beautiful examples of this that has ever been discovered. It is a rule so simple that a child could understand the statement of it, yet so profound that even the greatest physicists cannot fully explain why it exists, and so powerful that without it, nothing we know would exist. Thank you for joining me on this journey. If this video made you think, if it changed how you see the world around you, if it gave you a deeper appreciation for the quantum mechanical foundations of reality, please share it with someone who would enjoy it. Subscribe to this channel if you want more explorations like this. Leave a comment telling me what other fundamental mysteries of the universe you would like me to explore in this depth. And remember, every time you sit down and feel the solid surface of a chair, that is the Pauli Exclusion Principle saying hello. Before I end, let me share one last stunning piece of this puzzle. There is a deep connection between the Pauli Exclusion Principle and the arrow of time. The second law of thermodynamics tells us that entropy, the measure of disorder in a system, tends to increase over time. This is why time has a direction. This is why we remember the past, but not the future. This is why things age, decay, and run down. But where does this directionality come from? At the most fundamental level, the laws of physics are almost entirely time reversible. If you film a basic particle interaction and play it backwards, you get another valid physical process. So where does the irreversibility come from? Part of the answer lies in statistics. There are vastly more disordered states than ordered states, so random evolution tends toward disorder. But the statistics are different for fermions and bosons. Fermions, because of the exclusion principle, fill up states in a specific ordered way. They are forced into higher and higher energy levels. This ordering creates a baseline of structure that the second law can then act upon. Without the exclusion principle forcing matter into complex structures, there would be far less order to begin with, and the concept of increasing disorder would be much less meaningful. Moreover, the Fermi-Dirac distribution function, which describes how fermions populate energy levels at finite temperature, has a specific shape that is different from the Bose-Einstein distribution for bosons. This shape determines how electrons contribute to the thermodynamic properties of materials, including their entropy. The exclusion principle limits the number of electrons that can participate in thermal processes to those near the Fermi surface, which is why the electronic heat capacity of metals is much lower than you would expect classically. The exclusion principle constrains not just the spatial structure of matter, but also its thermodynamic behavior, which connects to the deepest questions about time and irreversibility. And here is something else to marvel at. The universe began in a state of extraordinarily low entropy. The Big Bang produced a smooth, uniform hot plasma. As the universe expanded and cooled, atoms formed, matter clumped under gravity, stars ignited, and complexity grew. The exclusion principle was there at every step. When atoms formed, the exclusion principle determined how electrons arranged themselves around nuclei. When matter clumped under gravity, the exclusion principle determined when that clumping would be resisted by degeneracy pressure. When stars formed, the exclusion principle determined their structure and evolution. The arrow of time, the growth of complexity, the emergence of structure, all of these cosmic processes have the exclusion principle as one of their essential ingredients. So here we are, you, sitting somewhere on some surface held up by the Pauli Exclusion Principle. Your brain functioning because of molecular structures organized by the Pauli Exclusion Principle. Comprehending these ideas using neurons whose ion channels depend on the Pauli Exclusion Principle. In a universe whose complexity and arrow of time are shaped by the Pauli Exclusion Principle. It is one rule, stated in one sentence, and it is everywhere. It is in every atom, every molecule, every star, every thought. It is one of the most fundamental facts about reality. And nobody can tell you why it is true in a way that satisfies the intuition. It simply is. The universe is built this way. And because it is built this way, we are here to wonder about it. That is the beauty of physics. Simple rules. Infinite consequences. 1. Prohibition. Endless complexity. The Pauli Exclusion Principle is not just a rule about fermions. It is a key to understanding why the universe is interesting rather than boring, why it is complex rather than simple, why it contains stars and planets and life, rather than just a uniform soup of featureless particles. It is, in a very real sense, the reason anything interesting exists at all. And with that thought, I will leave you. Think about this the next time you look at the night sky. Every star you see is held together by gravity and nuclear fusion, but its structure is determined by the exclusion principle. Every planet you know of is made of atoms whose properties come from the exclusion principle. And you yourself, standing on one of those planets, looking up at those stars. Thinking these thoughts are the most complex expression of the Pauli Exclusion Principle that we know of. A collection of fermions, obeying this one simple rule, arranged in such intricate complexity that they have become aware of themselves and the rule they obey. If that is not magnificent, I do not know what is.